Hello and welcome back to The Rest is AI. Today I'll talk about one of the most foundational topics in AI, that is artificial neural networks, or ANNs for short. If you have ever wondered how computers can recognize faces, translate languages, or even drive cars, neural networks are often the reason. In this video, I'll start from square one, what ANNs really are, then walk through how they are really inspired by human brain, maybe cover some complex mathematical equations, cover training and common architectures, and finally look at where they really shine and where they struggle. By the end, you will have a solid understanding of how ANNs actually work. So let us jump in. First things first, what exactly do we mean by artificial neural network? At its core, an ANN is a computing system made up of layers of simple processing units called neurons. Each neuron takes in one or more inputs, applies a simple function, and passes an output to the next layer. You can think of it like a giant network of decision makers. In a typical network, you have an input layer that receives data, one or more hidden layers where the thinking happens, and an output layer that produces your final result. The magic comes from how those neurons are connected and how they learn to adjust their connections based on example. Artificial neural networks borrow their name and inspiration from the human brain. In our brain, a single neuron has dendrites that receive signals, a cell body that processes them, and an axon that sends out a signal if the combined input crosses a threshold. ANNs mimic that with a mathematical model. Inputs get multiplied by weights, summed together, and then passed through an activation function that decides whether the neuron fires. It's a loose analogy, but it helps explain why we talk about layers of neurons and use terms like training or firing rates. Now, obviously, human brains are far more complex, but this abstraction gives us a surprisingly powerful tool for computation. The simplest kind of neuron in ANNs is called a perceptron, which was introduced back in 1950s. A perceptron takes inputs, multiplies each inputs by weight, sums them up, and then applies a step function. If the sum is above some threshold, the perceptron outputs 1, otherwise it outputs 0. Perceptrons can solve simple classification tasks like deciding if a point lies above or below a point, but they are limited. You cannot get them to solve more complex problems, and that is where multi-layer networks come in. To stack perceptron into deeper network that can solve complex pattern, we need nonlinear activation functions. Now I'm going to discuss three most common activation functions, but this is not going to be an exhaustive list. First one is sigmoid. It squashes your input into a range between 0 and 1. It is great for probabilities but can suffer from vanishing gradients. Now what is the vanishing gradient? Well, that's a title for another video. Second is tanh, similar to sigmoid but ranges from -1 to 1. Often works better in hidden layers since it is 0 centered. And third is relu. It outputs 0 if the input is negative, and it outputs the input itself if it is positive. It's simple, fast, and helps with training deep network. Now there are many more activation functions. Each has their own trade-offs, but industry standard these days is relu. But variants like leaky relu or ELU are also there if your network is dying. When we talk about deep learning, we literally mean networks with many layers. A shallow network might have one hidden layer, whereas a deep network might have dozens or even hundreds of this hidden layer. So the question is, why go deep? Because each layer can learn progressively more abstract feature. For example, in an image classifier, the first layer might detect edges, the next layer might detect simple shapes, following layer might detect textures, and so on. Until the last layer that can recognize whether the picture that you have given, whether it has a cat or a dog. That hierarchical feature learning is what makes deep learning so powerful. Now let us walk through a forward pass or forward propagation. What does it do? Let us consider the first, that is the input layer. That is the layer where you are going to feed your raw data, maybe a flattened image vector. Second is the hidden layer. At each neuron, multiply inputs by weights, add a bias term, and then apply the activation function. Pass that output to the next layer. Then you have an output layer where you get a set of activation. For classification, you might apply a softmax function to turn raw scores into probabilities that sum to 1. All of this is just a series of matrix multiplication and non-linear transformation, but it is embarrassingly parallel, which is why GPUs accelerate neural networks training so well. To train the network, we need a way to measure how far its predictions are, that is our loss function. Common choices include mean squared error for regression task and cross entropy for classification. Once we compute the loss, we use backpropagation to figure out how to adjust each weight to reduce that loss. Here is a breakdown. First, compute the loss at the output, then work backward layer by layer, computing the gradient of the loss with respect to each weight. Third, use an optimizer such as SGD or Adam to update the weights in the direction that lowers the loss. You do not need to know the full calculus if you are using a library, but it is good to understand that training is basically a guess, adjust, repeat cycle on a massive scale, which you keep on repeating until you get a optimum output. So far, what we have covered are fully connected or feed-forward networks, where every neuron in one layer connects to every neuron in the next layer. But real-world tasks often need specialized architecture. First is convolutional neural networks, that is great for images and grid-like data. They use convolutional filters to detect local patterns and pooling to reduce spatial size. Second is recurrent neural networks, designed for sequences like text or time series. They maintain an internal state that captures information over time steps. And third is transformers. They use attention mechanisms to weigh the importance of different parts of the input sequence. They become the go-to for NLPs and are now making waves in the vision too. Each of these builds on the basic neuron concepts but adds structure that suits specific data types. Now, where do ANNs actually power products you use every day? Let us have a look at some example. First is computer vision, which is used in face unlock in your phones, self-driven cars, and medical image analysis. Speaking of medical image analysis, I have uploaded a CNN project, convolutional neural network project, on diagnosing pneumonia, where if we feed a CNN a chest X-ray image of a patient, it predicts whether the patient has pneumonia or not. I'll share the link in the description. Please check it out. It might be helpful for you. ANNs also power natural language processing. You must have heard of tools like Google Translate and voice assistants like Siri and Alexa. They are also used in speech recognition, that is converting spoken audio into text in real time. ANNs also play a role in recommendation systems as well. Netflix, Amazon, Spotify, all of them, they use deep network to predict what you might like next. ANNs are also behind generative models, which can create realistic images, music, or even code using GANs and diffusion models. If your daily life involves an app that just works in a smart way, there's a good chance a neural network is powering it behind the scenes. If you are just starting out with ANNs, here are some practical tips. First is to start simple. Try a small feed forward network such as MNIST before jumping into big CNNs. Second, use appropriate frameworks, that is TensorFlow and PyTorch handle the heavy lifting. Read their tutorial and build end-to-end examples and projects. Third is to visualize. Plot your training and validation losses. Watch for overfitting or underfitting because they are very crucial. Fourth is to experiment. Tweak one hyperparameter at a time so you know what's making a difference. Lastly, learn the math. Understanding gradients, derivatives, and linear algebra will pay off when things go wrong. And there you have it, artificial neural networks from the ground up. I hope this gave you a clear mental map of how NS work, why they are so powerful, and where they fit in the AI ecosystem. Thank you so much for watching, and I'll see you in the next one.
It's not a game, it's a rich thing.